Hello, wonderful people. Here it is, chapter 14, satellite motion. Now we are in section 14.3, elliptical orbits. So, elliptical, that also means ellipse. And we've talked about that over the last week or so. That's the shape of a circle that's a little squished. And remember, there are 2 points around which you make an ellipse. And a satellite in orbit around Earth traces an oval shaped path called an ellipse. So a satellite in orbit around Earth traces out an ellipse. And that's how orbits really work. Uh, there are no circular orbits because the speed is always, it's like balancing an egg on the tip of a knife. You can do it, but if you go a little bit to the left or right, the egg rolls off. And it's the same thing with the circular orbit. If you have the exact perfect speed, then you're in a circular orbit, but you never get to maintain that exact speed perfectly, like balancing an egg on a knife. So, in the real world, all orbits are the shape of an ellipse. Get my arrows working. So, an ellipse is the closed path taken by a point that moves in such a way that the sum of its distances from two fixed points is constant. Ugh, that's the kind of definition a math teacher would love. The two fixed points in an ellipse are called foci. For a satellite orbiting a planet, the center of the planet is at one focus, and the other focus could be inside or outside the planet. So here's the experiment that I love to do, but we can't do unless you're in class. You take a piece of cardboard, put a couple pins in it, and then you take a loop of string. There's the knot that ties the string into a loop. And now you run around it, and your pencil keeps the string taut, and it makes an ellipse. It's just fantastic. In fact, let me go grab this. Here we go. Let me put this up there. Make it nice and big. Okay. So there, they're tying the knot in the string. There's the knot. Oops, what happened? Tying the knot in the string. There's the knot, nice and tight. So there's the knot. The two pins are in the cardboard, and they drew in the lines on the cardboard. And now they're just going to bring in the pen, and you pull the string tight. You see how it's tight when it goes all the way around, and bang, you've got an ellipse. So there's an ellipse. Now here's the focus, and there's the other focus. Those 2 points where the push pins are, that's the focus. Two focuses are called a foci. Oops, can I go back to where we're drawing it? So there. Now, do you see how this string and this string are always going to be the same total string, whether you're here or here? You know, the string, that part of the loop is always the same. So whatever's left over here is always the same. And that's how you get the shape of the ellipse going around. If you understand that, great. If not, that's okay. I'm just explaining how the ellipse is made. So this is a focus and this is a focus. In an orbit, the Earth is at one of those foci, and the satellite goes in this path. So it doesn't matter which focus the Earth is at, it's just at one of them. And if the Earth, if those two foci are close enough together, the center of the Earth can be at this one, but this could be inside the Earth if those two are really close together. I'm gonna have pictures for that coming up later. So I just wanted to show you there's the ellipse being drawn. And so that's that. And I really like doing that in person. It's a fun little thing to do. So the trick about the ellipse orbit, though, is now the satellite speed varies in an elliptical orbit. So you need to have 8 kilometers per second to get into an orbit, but they like to go a little faster just to have a little extra cushion. And once you're going more than the exact correct speed, Now the satellite overshoots the circular path and it moves away from the Earth and it loses speed due to the pull of gravity, and then it slows to a point where it falls back in. Let's do that in pictures. So here is the Earth. There's the satellite moving away from the Earth. Now, 8 kilometers per second would allow us to go in a perfect circle around the Earth. But we've given it like 9 kilometers per second, just to make sure. So it's going to go out here, and it's overshooting the circle that would keep it nice and close to the Earth. So now, while it's going out here, the Earth is, the gravity's pulling on it, and it's slowing it down. So it slows down to a little less than 8 kilometers per second. Now, it doesn't have enough speed to get away from the Earth up here. It's like, actually, it's more like 7 kilometers per second. So it's going to keep going this way, but it's going to fall back in. And as it gets closer to the Earth, it gets faster. So it goes faster, faster, faster until it's going fastest right here. Then it goes slow, faster, slow, faster. Do you remember this from the labs last week? I hope you do, because that was the point of the lab. This cycle repeats itself. It's going slow far away from the Earth and fast when it's close to the Earth. The center of the Earth is so here's the ellipse. The center of the Earth is at one of the foci, and you can imagine the other foci is probably right about there. So we're going to go back to the cannon example. If there's the cannon on the hill and it shoots and it lands, the cannonball lands on the Earth right there. If I wave my magic wand and the cannon could just travel through the Earth, the cannonball could travel through the Earth as if it was a ghost, but it still was affected by gravity. It would fall down, go around the Earth's center of gravity, and then come back up and go through the cannon, and it would orbit through the Earth like that. Now, I don't have a magic wand, so I can't make something orbit through the Earth. So I need to fire it sideways fast enough so that it gets around the Earth. And like I said, if I fire it at exactly that right speed, 8 kilometers per second, it will go in a perfect circle around there. But we always give it a little extra, we always give it a little extra speed. So now it's going to go up. So if we fire at 9 kilometers per second, it will go up, up, up till it's at 7, then it will fall back down and go faster. Are you seeing the connections here? So, okay. When the projectile traces a circular orbit, both foci are located together at the Earth's center. Again, if we had done the ellipse where you draw it, if you take the 2 pins and you put them on top of each other, now you're making a circle. But we don't do that. For elliptical orbits, the near focus is our center, and the location of the far focus is different for different speeds. So there's position A, B, C, D as it's going in this orbit. Where does this satellite have the greatest speed? Where does it have the least speed? So it's going to have the greatest speed when it's closest to Earth because it's going real fast here and then it slows and then it's at its slowest point here at C. And that's when it starts to fall back towards the Earth. So it gets more speed here and then it's fastest here, slow, 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 slowest there. What is the shape of the path of a satellite in an orbit around the Earth? An ellipse. All right, and then we go into section 14.4. We will save that for Tuesday. And all we're doing there is talking about kinetic energy and potential energy. So that's going to be a pretty easy day. Okay, thank you so much.